Hey everyone, in this section we're going to start talking about polynomial arithmetic. First, let's cover some polynomial anatomy. We want to understand what a polynomial is and how it's expressed mathematically. A polynomial in the variable x may be expressed in the following way. Here, every exponent is going to be a non-negative integer, and all of our a's with subscript represent some kind of coefficient. So a polynomial could look like 2x squared plus 3x. But let's break this down a little bit. First, we have a name for the largest exponent of a polynomial. We call this the degree of a polynomial, in which case what we're looking at is an nth degree polynomial. Next is the entire first term, that an x to the n. This is known as the leading term, and is the term that is accompanied by the largest power in the polynomial. We'll see in Chapter 3 when we begin graphing why this leading term is so important. The coefficient of the leading term is called the leading coefficient. And lastly, that term a naught, or a with a subscript of 0, is known as the constant term. Sometimes polynomials are written in what is called standard form. This means that the powers are arranged in descending order. So take the example 3x squared minus 7x to the fourth plus 1. It's not in standard form, but I can rearrange the terms, and I can also make visible the powers of x that I don't see. So my a sub 3 and my a sub 1 are actually 0 because I don't actually see an x to the power of 3 or x to the power of 1. And now that I've arranged things, I see that the leading term is negative 7x to the fourth, the leading coefficient is negative 7, and that the degree is 4. Some of our examples will address what is called a multivariate polynomial. In other words, a polynomial with several variables, but each exponent is still a non-negative integer. For a multivariate polynomial, you calculate the degree by looking at the power sum of each terms. So I have a term of 3x to the first y squared, and another term of minus 7x squared y squared. The highest power sum is going to be 4, which comes from that minus 7x squared y squared. So I would call this a degree 4 multivariate polynomial. We bring this up, namely because when we have problems where we have to combine like terms, we might have a lot of variables happening at once. Just know that we can only combine terms if all the variables and exponents therein are identical. So for example, if I have the expression 2x y squared z cubed minus 4x y squared z cubed, I can combine those by subtracting the coefficients simply because every variable and every exponent is identical. I cannot do the same thing with the term 2x y squared and z cubed and negative 32x y squared z squared. Even though all the variables match and all the exponents almost match, the powers of z are different, so these don't combine. Again, I can only combine terms if every variable and every exponent is identical. And I'll give a word of caution here. We got to be careful about when terms look similar, but they aren't actually like terms. For instance, xy squared and x squared y. They look very, very similar, and it's very easy to mistakenly combine them when in fact they are different and they don't combine. It's a very good idea to take every term and rearrange all the variables so that they are in alphabetical order. The commutative property of multiplication lets us do this, and it makes it easier to see what exponent goes on what power and which terms are actually like. In this next set of examples, we'll add and subtract polynomials. So we're going to take 3 times minus 4x cubed y plus 2xy minus 3y subtracted from 4 times 2xy plus 3y plus x squared plus z. And believe me, you had just as much fun listening to that as I had saying it aloud, and it definitely took a couple of tries. But I'm making a point, which is that you have a lot of terms here, you have a lot of arithmetic to do, so good bookkeeping and good algebra is very important. Order of operations is key here. Nothing inside the parentheses simplify because I have no like terms, so our first step will be to distribute that 3 and that negative 4. Doing so gives us the following. I'm going to get minus 12x cubed y plus 6xy minus 9y. Now I distribute the negative 4, and I got to remember to take that negative sign with me. So that's going to give me negative 8xy minus 12y minus 4x squared z. And now that my numbers are distributed, I have to go through and make sure there are or aren't any like terms to combine. I notice that I have 6xy and negative 8xy. I also have minus 9y and minus 12y. Those are all only terms that combine. The rest don't simplify. And once I combine these terms, I get negative 12x cubed y minus 2xy minus 21y minus 4x squared z. And we're done. For our next example, we're going to look at a squared b plus 2ab plus ab squared minus the quantity ab squared minus 5ab minus a squared b. Again, we have order of operations, but no terms within either set of parentheses actually combine. I don't have any like terms, so that means that I can distribute anything outside the parentheses and then drop them. That first quantity doesn't have anything out front, so I can just drop the parentheses. But the second quantity has a negative that needs to distribute, so let me go ahead and do that. As we distribute terms and drop parentheses, we get a squared b plus 2ab plus ab squared minus ab squared plus 5ab plus a squared b. And we'll notice that we have a lot of things that actually combine here. The 2ab and 5ab, the ab squared and minus ab squared, and then the very first and last terms. This all simplifies to 2a squared b plus 7ab, and we're done. So the things to remember here is to be careful of exponents, namely be careful when you're trying to combine different terms, and also make sure to distribute those negatives outside parentheses. Now that we have a few examples under our belt of addition and subtraction, let's look at examples with multiplication. We're going to warm up to this idea by multiplying x squared with 5x plus y. We know that we can distribute the x squared term just like a number. This is going to become x squared times 5x plus x squared times y, and by using our properties of exponents, we get 5x cubed plus x squared y. The reason I say this is a warm-up is to set a precedent that says I can multiply a polynomial using the distributive property, and yes, x squared by itself does count as a polynomial. And we can do the same thing with the quantity x plus 1 times the quantity 3x plus y. Normally I could FOIL this out, but we're going to see pretty soon that foiling does not always work. So let's approach this with a distributive property mindset. What we're going to do here is take the quantity x plus 1 and distribute it across the quantity 3x plus y. When we do so, I get 3x times x plus 1 plus y times x plus 1. If this does look strange, remember we just did the same thing upstairs with the x squared. I can distribute an entire quantity even though it's a sum. If I'm distributing anything across the 3x plus y, that right term, then 3x is going to get something and y is going to get something. It's just in this case that something is the entire quantity x plus 1. Now I just distribute the 3x and the y across the x plus 1 terms. Once I distribute and simplify using properties of exponents, I'll get the final answer of 3x squared plus 3x plus xy plus y. I don't have any like terms, so nothing combines, and we're done. And this works both ways. I could have distributed the entire 3x plus y term across x plus 1. When I do this and I simplify, I'll see that I get the exact same answer that I got before. So again, the whole point of this multiplication idea is that I can use the distributive property even with terms that look like x plus 1 or 3x plus y. Let's jump right into a more challenging example. Let's look at 3a squared b plus 2a minus 3b times the quantity ab squared plus 7ab. That first quantity has 3 terms and that second quantity has 2. So automatically I realized that I couldn't even use FOIL on this if I wanted to. But that's why we have the distributive property. We are now equipped to handle something like this. We are going to choose to distribute that term on the right, that a b squared plus 7ab. I've got 2 terms here. I could have distributed any one across the other. So my choice of distributing ab squared plus 7ab across the left term is just that, it's a choice. You get the same answer either way. I personally just choose to distribute the smaller term. But each term in that left factor is going to be multiplied by ab squared plus 7ab, and when we expand it all out, we obtain the following. These problems tend to have a lot of moving parts, so just remember to do things one step at a time. I'm going to do the individual distributions for each of the 3 terms. First, I'll distribute the 3a squared b, then the 2a, then the negative 3b, remembering to bring that negative sign with me. And honestly, don't be a hero. What I mean is, don't try to do the arithmetic in your head, don't try to do the exponential arithmetic in your head, just write it all down as multiplication as you're getting used to this process. The more practice you'll have, you'll know what steps you can do in your head, but for now, write everything out explicitly and then simplify. This minimizes errors and it just gets you a better bookkeeping process at the beginning. But once I start multiplying my numbers and adding my exponents, I'll get the following expression. And it turns out that even though I have a lot of a's and b's with different numbers, none of these have the same terms. I have no like terms, so there's no more simplification that needs to be done, meaning we're done with this problem. For our next example, we'll multiply y squared plus x times the quantity 3y squared minus y plus 1. My personal preference is to distribute the left factor because it has fewer terms. So I'm going to distribute the y squared plus x across 3y squared minus y plus 1. And what I get is the following quantity. Next, I'll distribute the individual terms, the 3y squared, the negative y, and the 1. This is going to give me the following. I simplify all my numbers and my exponents, and I get this last line. And even though it's not written in the screen, that plus 3xy and the minus xy do combine. So that's what we have for polynomial addition and multiplication. In our next video, we're going to talk about polynomial factoring.